Good morning. We already discussed yesterday about fine particles of dust when distributed in air, and if some ignition source is present, the dust particles, since they are of small particles, they readily volatilise, release the, let us say, the hydrocarbon vapor if it is organic. This hydrocarbon vapor mixes with air, forms a combustible gas which can then burn or which can detonate, and in which case we can also have something known as dust explosions. We also learned how to estimate the concentration of dust, which we said had units of kilograms per meter cube. For the particular case when dust falls under gravity or when it is forced by air, like it is under forced draft in a pipe when dust is smeared all along. Having learned how to determine the concentration of dust, and also beyond a certain concentration of dust in air, we found that it's an explosive. We wanted to determine what is the type of ignition possible. We wanted to determine what is the ignition energy required to start off a dust explosion. We readily find, since dust is initially in the solid state, smeared in the air, and the duty of the ignition source is first to make sure that the dust particles release the hydrocarbon vapor, or if it is some other substance, release the vapor of the particular substance. Well, the minimum ignition energy for the dust particles should obviously be greater than the minimum ignition energy of the same vapor, or let us say in this case it releases hydrocarbon gases, it will be greater than the minimum ignition energy of the particular gas in the air mixture. Therefore, we say, well, minimum ignition energy of dust is expected to be greater than the minimum ignition energy of the gas. And when we say dust, dust is normally denoted by the symbol ST. The symbol ST comes because a lot of work on dust explosions happened in Germany, and they are pioneers in dust explosions, and dust in German is known as Staub, S-T-A-U-B. Therefore, we show the value of minimum ignition energy, ST meaning dust, is greater than minimum ignition energy for a gas. For the same gas mixture, for the same dust air mixture, the minimum ignition energy for the dust air mixture is greater than for the gas mixture. For a gas, we said, well, I need to form a flame kernel. The flame kernel has to be of the size greater than the quenching distance, and around the flame kernel, what is it we have to do? We have a thickness of the flame which is to be ignited by this particular kernel of gas, and therefore the minimum ignition energy corresponds to the volume, that means the thickness of the flame around the flame kernel which must be ignited, and this is how we estimated the minimum ignition energy for a gas. If we have to do the same thing for a dust mixture, what is happening? I am talking of a kernel of ignition for a dust mixture, and around it, I have the dust particles, and the dust particles have to initially vaporize and mix. Therefore, the expected thickness of the flame is going to be larger. In other words, the thickness of the flame is going to be more for the dust air mixture than for the equivalent gas mixture, and since the flame thickness is larger, I require a larger kernel size to be able to ignite it, and the volume of the gas which is required, or the energy required, must correspond to the diameter, that is the surface area, into the particular thickness over here, and therefore the minimum ignition energy for the dust mixture will be much greater than for the equivalent gas mixture. Having said that, to estimate the thickness of the flame in a dust air explosion or dust air flame is going to be more difficult than we estimated it. Mind you, for a gas we estimated is equal to the thermal diffusivity divided by the flame speed. It is going to be more difficult, and we experimentally evaluate it in some apparatus known something similar to the Hartmann tube. What is this Hartmann tube? It consists, it's a modification of the original Hartmann tube, in which it is a straight pipe. At the bottom of the pipe, what you do is you have a shape like this. No, so you have a shape like this on which maybe the dust particles are given over here. A mass of all the dust particles are accumulated over this particular shape, and the diameter of this particular tube is typically around 3 centimeters, and the length of this particular tube is something like 60 centimeters, giving the volume of this tube is something like 1.2 liters. Now, what is done is, through this particular shape, what is done is you allow compressed air to come. This is all porous bottom surface, and you allow the compressed air to blow the dust into the mixture, typically at a pressure of around 4 bar or so. It is forced, and what happens, the dust comes up along with air. You form a dust air mixture in this particular enclosure. This is a transparent pipe, and into this transparent pipe or tube, as it were, what you do is you provide something like, at a distance of something like 1 centimeter from the bottom, you put 2 electrodes and create an electrical spark, something like this. You create an electrical spark over here. How do you do that? You connect the electrodes to a capacitor which is charged to high voltage, and this capacitor discharges across these 2 electrodes. That means I will have something like a power supply which charges the capacitor to high voltage, and then you discharge it, and the energy released by the capacitor charged to high voltage is something like half capacitance into V square. Therefore, I know the energy which is released in this gap. I disperse the mixture in this particular volume, as it were, and then I find out what is the minimum energy required. I do a series of experiments, find out when it ignites, and I slightly reduce the energy, make sure that for the reduced energy it does not ignite at all. Maybe in 11 out of 10 experiments it must not ignite at all, and therefore I determine the minimum ignition energy for the dust explosion. Therefore, I know how to create the minimum ignition energy, and since the thickness of the dust explosion is much larger than a flame, and we also say intuitively that the minimum ignition energy is greater than for the gas things, when we find that the values are something like 2 orders of magnitude greater, that means something like almost 100 times greater than for 2 orders of magnitude greater than minimum ignition energy for a gas mixture. Now, when we look at the gas mixtures, we found for something like hydrocarbon mixtures like methane, for something like propane air mixtures, methane air mixtures, the ignition energies were between 0.20 millijoules, something like 0.4 or so millijoules. And when we talk of dust air explosions, the ignition energies are typically between 220 to 100 millijoules. That means typically about 100 or larger. Therefore, we find, well, to ignite a dust air explosion is not going to be that easy as it is to ignite a gaseous mixture. But then we must realize that yes, in practice, yes, we do get such type of energy release. Maybe if we have bearings which are supplying the dust to be hot, well, I can have these type of ignition energies. I could have electrical sparks which can deposit energy by arc discharge, which are typically of a few 100 millijoules. I could even have, in a dusty environment, supposing somebody is having a grinding wheel and sparks are flying, well, the sparks from the grinding wheel can as well initiate a dust explosion. And dust explosions are initiated and are a source of problem, like what we discussed yesterday. It happens all the time in food industry. However, if the confinement is open, that means unconfined geometry, then in that case, the occurrence of dust explosions in an unconfined geometry, like in a very open space, just because it relaxes, it's not possible for dust to be collected and we need a certain minimum ignition energy or an ignition time, and during that time, what will happen in an unconfined geometry, that dust particles may not be there to sustain the ignition, and therefore in an unconfined geometry it is not possible, but any confined or partially confined geometries, well, dust explosion is a source of danger. Therefore, we say yes, this is all what we learned. We learnt about finding the concentration. We also talked of minimum explosive concentration, what is required to cause the dust. We related it, the minimum explosive concentration, to the diameter of the dust particles. Can we go ahead from this and put all the things together? Like for instance, yes, we talked in terms of minimum explosive concentration. We also talked in terms of, today we were talking in terms of minimum ignition energy for a dust mixture. Therefore, we are talking of minimum ignition energy. Minimum ignition energy, MIE. We talked of MEC, minimum explosive concentration. Are there some relations, like for instance, when we had the gaseous mixtures, we plotted percentage volume of the fuel vapor or volume of fuel in the volume of the mixture as a percentage of minimum ignition energy for a gas, and we found below some threshold value of the fuel in the volume of the mixture, the gas just does not ignite. We also said above a certain threshold value, well, the gas does not ignite. And when the gas does not ignite, what does it imply? Well, even if I give infinite energy, the gas cannot ignite, and therefore the shape of the minimum ignition energy versus the percentage volume of the fuel in the volume of the mixture has a typical curve, something like this, followed by a flat bottom. That means I have a U-shaped curve. This is the type of curve we have of minimum ignition energy for a gas versus the percentage volume. Is it possible to generate an equivalent curve for, let us say, minimum explosive concentration for a dust mixture, ST, for minimum ignition energy for a dust explosion, dust we said is ST, and therefore, what will this curve look like? Can I plot some equivalent curve here? Therefore, let us try to plot it over here. Well, I have concentration here. I talk concentration of the dust particles, let us say in so much kilogram per meter cube. I talk in terms of minimum ignition energy for a dust mixture in terms of, let us say, millijoules, because the energy level is of the order of millijoules. Then what is going to happen? We said just like in a gas mixture, we also found yesterday that, well, below a certain threshold value of concentration, well, the mixture just does not ignite. What happens is this is something which cannot ignite at all. How did we come to this? We said, well, I plot the diameter of the dust particles over here. I plot over here the minimum explosive concentration, MEC, for the dust mixture, and what did we find? Well, if the diameter is quite small, well, I have some minimum concentration is required such that flammable vapor air mixture can form just at the limits of flammability, and therefore I require some minimum explosive concentration when the diameter is typically less than around 100 micron or so. Below 40 micron it is constant, above that it slightly increases, and when the diameter exceeds something like 120, 130 microns, well, the particles of dust can no longer vaporize and form this mixture, and this is the type of curve we have. Therefore, this is the absolute lower value corresponding. That means I must have minimum explosive concentration corresponding to this, and this is the value what is given. This is equal to MEC over here, corresponding to the small diameter dust particle. And therefore, the energy for ignition, if I were to plot it on the same curve, well, over here the energy is very large. At this, I have a threshold value of ignition energy which comes like this. As I increase the concentration, well, I am able to form the gas. The minimum ignition energy is at this level. But the moment a large number of dust particles accumulate, well, it gets starved of air. Not only that, maybe you have pockets in which I have rich dust and weak dust, and with the result, the ignition energy goes up. Therefore, the shape of the curve is going to be a straight line followed by a line followed by an increasing line. For the typical case in which the diameter was less than around 40 micron, the dust particles, if the size of the dust particles went up, well, the minimum ignition energy goes up like this. Well, if it is the diameter is still larger, if the diameter is very large, ultimately if the diameter exceeds this, it cannot ignite. Well, this is the size of the increasing diameter of the dust particles. Therefore, we find, well, the minimum ignition energy for a dust particle corresponds to the case when for a threshold value of concentration exceeding some limits, but less than some limits, it is there, and this is the figure corresponding to the U-shaped curve corresponding to U and L lean flammability limits, upper flammability limits of a flame, and this is the type of figure what we should get for a dust explosion. It is time to go forward and try to see whether we can also get some figures for the maximum pressure, maximum violence of the explosion involving the dust mixtures. But before we do that, let us just spend a couple of minutes on maybe is detonation, which is much more violent than burning or let us say flame in a dust mixture, is detonation in a dust mixture possible? And if detonation in a dust mixture is possible, in the one-dimensional model of a detonation, well, we should be able to form a shock wave. A shock wave is formed by the ignition source. Behind the shock wave, well, you have the dust particles which volatilize, release the vapor has to mix with air, and then, well, the chemical reactions should go on, and it is these chemical reactions which occur behind the shock wave which should drive the detonation. Therefore, we say, well, immediately we will tell, we talked in terms of an induction distance behind the detonation, and we talked in terms of a one-dimensional model, which was the Zeldovich, von Neumann, Doring model of a detonation, ZND model of a detonation. Well, in this, the thickness of a detonation is large, but it is still possible under the condition that the total induction distance, if it is still not too large, it can still maintain a detonation at high speeds and cause a large value of pressure, and such type of detonations have been observed maybe in wheat flour. Mind you, we are talking of wheat which is ground, typical dimensions being 40 micron to 60 micron wheat flour, and for concentrations between 0.22 to 0.265 kilograms per meter cube concentration, well, detonation is possible. Why? Not only for wheat flour, we also have, in the mines wherein, well, let us say coal mine we take. In the coal mine, people remove the coal and in the process have the dust of carbon, coal dust is available. Therefore, you have coal dust. In the mine sometimes methane gas is also available, and this with air. That means dust along with the fuel gas and air also form severe detonations at high pressure, and the dust explosions or dust detonations are also possible. Therefore, we say, well, dust is as dangerous as a gas as long as the dust size is less than some threshold value. If the dust particles are of large size, well, it is not a problem. But we also must remember that if the humidity of the medium is large, then it is difficult to volatilize the dust, and therefore maybe relative humidity, turbulence are additional factors which influence the formation of dust explosions. Having said these things, it is time to determine the maximum pressure from a dust explosion. Therefore, let us put this last point across. For the particular case of gas explosions, what did we tell? The maximum pressure of gas mixture in an enclosed vessel minus the initial pressure is equal to gamma minus 1 into the energy density, energy released in the particular volume of the enclosure, that is a fixed volume, divided by the the particular volume of the enclosure. That is a fixed volume of V, energy release or heat release is Q, gamma is the specific heat ratio of the gases, the maximum pressure is related through this particular expression. We also had an expression for dP by dt maximum into volume to the power 1 by 3 was equal to kg, where kg denotes the particular violence rate, the unit is equal to bar into V to the power 1 by 3 meter divided by T second, so much kg bar meter per second. And we said for hydrocarbon gases, typically the value is around 55 to 75 bar meter per second. For the case of hydrogen air mixture, it's much higher, of the order of maybe 100 or 110 bar meter per second. What are the values for the dust mixtures? For the dust mixtures, we would be interested in KST, we would be interested in the maximum pressure, and such maximum pressure and dP by dt, it's difficult to calculate. Like in the case of we did do these calculations. We use the internal energy of formation and calculated the value of Q. We calculated V. We were able to calculate this, and unfortunately for the dust mixture, it is a little more difficult. And again, what we do is we have the Hartmann tube, as it were. Now in this case, it's made of solid material. And in this case, the dimension is a little smaller, of the order of 60 centimeters length. It should be 30, because when we had the ignition test in the transparent, it was little larger. In this case, it's of the order of 30 centimeters. The diameter is around 3 centimeters. Again, we have the dust being smeared from the bottom. You allow the dust to get smeared. We allow an ignition source to ignite it, maybe a high voltage ignition source. And then we measure the value of pressure with respect to time. Rather, we determine the value of pressure as a function of time. Pressure gets started, reaches the maximum, and we measure the PM, that is the maximum value of pressure and the maximum value of dP by dt for the dust mixture. And where does the dP by dt maximum occur? It occurs at the inflection point, and at the inflection point you have a slope over here, and this slope is what is dP by dt maximum. Therefore, we measured this PM and dP by dt maximum, and we use this to calculate the net violence of a particular dust explosion. Let's see how to calculate it. Let us say the consequences of an explosion are the following. The two consequences are, well, I have a high pressure, I also have dP by dt into V to the power 1 by 3 is equal to KST, because it is dust, and typical values of KST for dust are somewhat higher than for hydrocarbon gas mixtures. Let's put some values for PM and dP by dt for the dust mixtures. Well, if I take the value, let's just consider 4 simple cases. Milk powder of small dimensions, typically 40 micron to 60 micron particle size of milk powder. The value of the maximum pressure, what we get, is something like 8.1 to 9.7 bars or atmospheres. If I have something like sugar, yesterday we talked of sugar, we said it is sucrose, and the values are very near to milk powder, 8.2 to 9.4. You find it's over a small region between 8.2 to plus minus 1 or so, right? 8.2 to 9.4. If I take wood dust, the scatter is even higher, because depending on the type of wood, namely you have something like 7.7 to something like 10. Mind you, all these are based on dust particles, the particle diameter being of the order of 70 micron. Somewhat, we are not talking of the very low threshold value of 40 to 50 micron, of this order. And if you say 74 micron, if I say the dust particle is 74 micron size, it means through a sieve of size 200, sieve size, I get a diameter of 74 microns. Therefore, corresponding to 200 is what is used as a standard. Therefore, you have wood dust, the peak pressure is 7.7 to 10. And the last one, we take maybe aluminum dust. The peak values are 5.4 to 12.9. These values, when we consider these are also hydrocarbon substances or organic substances, these are higher than the value of maximum pressure which we saw was between 5.5 to 7. This is the type of values we get for PM. When we take the values for the KST values, what is KST? Is equal to dP by dt maximum into volume to the power 1 by 3 is KST value, and the unit is bar meter per second. For the milk powder, the value is something like 58 to 180, well, a huge scatter, 50 to 200, that is the type of values. For sugar, it is also quite similar, 59 to 165 bar meter per second. When we talk of wood dust, well, it's a little higher, 83 to something like 211 bar meter per second. And for aluminum powder, well, the scatter is extremely large, something like 16 to 740 bar meter per second. Therefore, you find in all these cases, the scatter is large. In fact, the scatter for the KST value is higher than the maximum value what we determine in the experiments. And the reason for the scatter is, the thing is that, it's very difficult to have consistently the same diameter dust particles of same concentration in a given medium. And again, turbulence, maybe the effect of other factors, like you say the agglomeration in some particular place, turbulence tends to agglomerate, you have gradients, and these are factors which tend to scatter the results. And therefore, whenever we talk in terms of dust mixtures, there is a tendency to not talk of precise numbers, but to put in terms of classes of dust. What do you mean by dust, classes of dust? We said dust is denoted by the word St from German being Staub, and when we say St, corresponding to 0 class of dust is one for which, let us say, St classification, let me put that down, it's very simple. We say St classification of dust. We say when the St corresponds to 0, well, I say it corresponds to St 0. The value of KST corresponding to this is 0. That means there is no possibility of a dust explosion. That means the rate of pressure rise is 0. When I call of class 1, that means St1 class, we say, well, the KST value is between 0 to 200 bar meter per second. In other words, most of the organic substances like wheat flour, sugar, powdered sugar, maybe corn flour, most of the organic substances are within this range, which we call as St1 or the class 1 type of a dust. When we say St2, we mean values of KST between 201 to 300 bar meter per second. That means moderately high, and these correspond to something like wood dust, good wood, if in a fine powdered form can generate high pressure. We call it as second class or St2 type of classification, and St3 corresponds to KST value greater than 300 bar meter per second. That means these are a little violent and one must be careful. Essentially, the metal powders correspond to the higher values of KST, or rather when we say this is the KST values and we say that the classification is St3. Therefore, we classify dust into St0, St1, St2 and St3 for these depending on the KST values, and KST is dP by dt maximum into V to the power 1 by 3. However, we must remember one thing. when we talk of metal dust, it's not that the metals essentially volatilize and the volatiles of the metal burn, but in case of many metals, what happens is you are talking of surface combustion. And it is the surface combustion which dominates, and therefore we must be careful when we interpret the results of maybe metal dust which give rise to dust explosions. Having said that, let's go still further and try to see whether we can put the ignition, whether we can put the severity of the explosion. Having talked of PM and also dP by dTm, that means the maximum pressure and the maximum rate of pressure rise. Well, we say when an explosion takes place, rather when a dust explosion takes place, you have maximum pressure, you have the maximum value of dPt by dm, and therefore I can now define explosion severity of an explosion. That means the consequences of an explosion depends on the severity, and it is more severe when the PM value is high, that is the maximum pressure is high, when the value of dP by dt maximum is high. Therefore, I can say, well, the explosion severity will be proportional to the maximum pressure and also the value of dP by dTm. That means the explosion severity is the product of PM into dP by dt maximum value. If I say, well, the consequence of an explosion can be seen by this particular expression, it does not tell us, it tells us only about the consequences, but it does not tell us anything whether the explosion is likely to occur. That means even though it tells if the explosion occurred, I would get an explosion severity of this order, it does not tell us on the likelihood of an explosion to occur. And for likelihood of an explosion, maybe I must have the explosion to occur. That means if the minimum ignition energy is small, that means minimum ignition energy of the dust mixture is small. If the minimum explosive concentration of the dust mixture is small, further, if the ignition temperature of the dust mixture is also small, well, it is more likely to get into an explosion. This just says if an explosion had occurred, the severity would be so much. But for the explosion to occur, well, these three things should be as small as possible. Or rather, what does it say? What is the ignition sensitivity? What is the likelihood of ignition taking place? Or rather, the ignition sensitivity of a dust explosion to occur should go as small, 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 or rather, it should go as 1 over minimum ignition energy for a dust mixture into 1 over minimum explosive concentration for a dust mixture into something like 1 over minimum ignition temperature, the minimum explosive concentration for a dust mixture, minimum ignition temperature for the dust mixture. This will be proportional to the, let us say, ignition sensitivity I denote by IS. Well, IS should be proportional to this. See, we have talked how to determine the minimum ignition energy using the Hartmann tube, which is a transparent form of Hartmann tube. We said, well, I can determine minimum explosive concentration in the same experiment by finding the concentration at which it ignites. To get the temperature of ignition, we use a furnace, and this furnace is called as the Godbard Greenwald furnace. In this furnace you have something like a pipe or something like this. You have a particular material here which is at constant temperature. The temperature can go to something like up to 800 degrees centigrade. You allow a particular dust mixture to pass through, and when the temperature of this particular central piece, which is kept at constant temperature, is able to sustain the ignition right up to when the dust reaches the bottom, we say that should correspond to the ignition temperature. That means the temperature of this particular rod here, which is kept at uniform temperature, is able to ignite the gas, and this is how we estimate the temperature of ignition. It's also possible in Germany, they have used maybe a horizontal configuration of a similar system in which the dust mixture is allowed to come and fall on this constant temperature rod or an object. And when this happens, there is some level of accumulation, and we saw when there is some accumulation, what happens is initially you could have something like sublimation taking place, and afterwards there could be a flashover, and after a flashover there could be something like a secondary explosion, and therefore the temperature what is measured in this particular configuration tends to be a little lower than this. However, we always say, well, an ignition temperature could also be measured, and the ignition sensitivity is proportional to this. Therefore, we are saying, well, explosion severity is product of Pm and dP by dTm. Ignition sensitivity is product of 1 over minimum ignition energy, 1 over minimum explosive concentration, 1 over the ignition temperature, product of these three. But we find there is a lot of scatter in these particular results. What we obtained, we saw some values, dP by dt scatters over a large range, Pm there is smaller scatter. Similarly, there is scatter in temperature of ignition, and therefore it becomes desirable when we define explosion severity, namely as a consequence of the explosion, and ignition sensitivity as the ease with which an explosion, a dust explosion could occur. Can we put some standard and compare it with respect to some standard so that these things become more meaningful? And that's what we will do now. And the standard which is adopted is what we call as the Pittsburgh coal. It is a 74 micron sized coal dust and the coal which is used is the Pittsburgh coal mined from Pittsburgh, because each coal has its own characteristic. And the values of the Pittsburgh coal which are used are the temperature of ignition of the Pittsburgh coal is something like 610 degrees centigrade. The minimum ignition energy of this coal dust is 60 millijoules. The minimum explosive concentration is equal to 0.055 kilogram per meter cube. The maximum pressure of this particular coal dust is equal to 6.5 bar, and the value of dP by dt maximum is equal to 156.5 bar per second. This is the standard with which we compare, and therefore, if we have any other sort of a dust mixture, we would like to compare it with this particular Pittsburgh coal which is of 74 micron size. And therefore, how will I now define my explosion severity and ignition sensitivity? Let's get started with the ignition sensitivity. Therefore, how will I define? Well, I know ignition sensitivity is given as the inverse of one over MIE for the dust mixture, 1 over the minimum explosive concentration for the dust mixture, 1 over Ti for the dust mixture. And now, if I were to say this is for, let us say, any dust mixture, and now I want to say what is the ignition sensitivity for this particular dust mixture. Therefore, it is going to be 1 over this particular expression, let us write it again, 1 over MIE into 1 over MEC into 1 over Ti for the given dust mixture, divided by 1 over, I have minimum ignition energy into minimum explosive concentration and the ignition temperature, all for the standard coal dust of standard Pittsburgh coal dust of 74 micron size, and this becomes the relative ignition sensitivity of this dust mixture, which works out to be MIE into MEC into Ti for the particular case of the Pittsburgh coal, divided by MIE into minimum explosive concentration into ignition temperature for the particular dust mixture which we are evaluating, and this becomes the ignition sensitivity. Now, I would like to generate some numbers for this, but let us put the definition for explosion severity and then put the number together. If I were to similarly take the case of explosion severity, well, we know, yes, it depends on the consequences. We are looking at Pm into dP by dm, and therefore, when we say explosion severity, we are talking of Pm into dP by dTm for the particular dust mixture, let us say, divided by, I want to compare it with the Pittsburgh coal, I have Pm for the Pittsburgh coal, dP by dt maximum for the Pittsburgh coal, in the denominator is for the Pittsburgh coal. And well, the values for the Pittsburgh coal are available. We just looked at the value of Pm. We say Pm is around of the order of something like 6.5 bar dP by dt is equal to something like 156.5 bar. Similarly, we know the values of the MIE, MEC for Ti, and if I can determine the values for my dust mixture, I can find out the relative value of explosion severity and the explosion and the relative values of the ignition sensitivity. Let us put down the values of the ignition sensitivity. Let us put down the values of explosion severity for a few cases in which we are comparing it with the standard coal mixture. When we find that the ignition sensitivity is of the order of 0.2 for a given dust mixture, maybe it could be from something like 0.2 to 1, it could be between 1 to 5, in which case it is, this is a relatively weak one compared to a Pittsburgh coal. It is 1/5 of this, therefore it's a, let's say it's a something like a weak explosion, that is, it is weakly sensitive. It does not immediately get into a sensitive. It does not readily get into an explosion. 0.2 to 1, it is somewhat tending, that it is, let's say, medium. 1 to 5, well, it's much stronger than the Pittsburgh coal. If it is much greater than 5, well, it tends to be very severe compared to the Pittsburgh coal. Therefore, these are the relative gradings of ignition sensitivity, and depending on the mixture what we have, if the mixture is between 0.2 to 1, it's medium, and most of the cases of our organic flowers fall in this category. Wood dust falls in this category, and when we say severe, metal dust and some other substances fall, some other dust fall in this particular category. When we talk of explosion severity, the values are somewhat different. If it is less than, let's say, 0.5, well, it's not as sensitive as Pittsburgh coal. If it is between 0.5 to 1, well, it tends towards the Pittsburgh coal, it's medium. When it is 1 to 2, the explosion severity is 1 to 2, it's stronger than Pittsburgh coal, must be careful. If it is greater than 2, well, it is much more severe than Pittsburgh coal. But some people, instead of using to evaluate the sensitivity based on ignition sensitivity, that is the proneness for the explosion to occur, and consequences of the explosion through explosion severity, they define another term, and that another term is known as index of explosibility. What we mean by index of explosibility is, we want a single term, this is something like likelihood and the consequences. We want the net hazard of a dust explosion to be very clear. That means we must include both the sensitivity and the consequences together, and the index of explosion denoted by IE is product of the ignition sensitivity and explosion severity. That means ignition sensitivity into explosion severity is index of an explosion, and therefore putting these figures together, we tell ourselves if the index of explosibility, the value is less than 0.1, 0.1, well, the hazard is small. Well, it's either not likely to get into a dust explosion, and even if it gets into an explosion, the maximum pressure and dP by dt are not going to be very severe. Therefore, we say, well, hazard is small. If the value is between 0.1 to 1, then in that case, well, there is a significant hazard. that means we are talking of a moderate hazard. The hazard is almost similar to what a Pittsburgh coal dust has, its moderate hazard. If it is between 1 to 10, that is the index of explosibility is 1 to 10, well, it is a strong case, it's a strong hazard, must be careful to use it, because the consequences as well as the sensitivity are large. If it is greater than something like 10, well, it's severe and one has to guard against such dust explosions. And this is the way we categorize the explosions in terms of index of the explosibility as it is for a dust mixture. Therefore, this is all about dust mixtures, and in the dust mixtures what we learnt are, yes, it is possible to have explosions in dust air mixtures, especially if the dust particles are small. The food industry, especially, we talk in terms of different organic substances. We also talk in terms of different types of dust, maybe the wood dust, maybe the other types of dust which are available. They all can explode, and if it explodes, you have a large value of PM, large value of dP by dt. That means you have explosion severity which is high, and therefore maybe dust explosion requires attention. It has not been theoretically sorted out the way we have been looking at gas phase explosions, but there are a number of experiments and modeling going on, and we also say, well, it can also detonate, in which case the hazard is much larger. The only relief what we get in dust explosions is, well, if it is unconfined, and in countries, that is in countries like India, wherein we handle foodstuffs in open, the chances of a dust explosion are not there, because we said, well, what happens is it is difficult to get sustained dust being there for a long time, and we are not able to get dust explosions normally in an unconfined geometry. To be able to put things together, let's do one small problem involving a dust explosion, such that the things we learned fall in place. And the problem I consider is, let's say I have a carpentry shop. In the carpentry shop, I during the different processes taking place in a carpentry shop, I generate wood dust. And this wood dust, let us say, is of mean dimension around, let's say, 50 micron size dust. The place gets littered with wood dust, and therefore I use a vacuum cleaner to remove this wood dust. And this vacuum cleaner consists of, let's say, a motor which generates a vacuum pressure of, let's say, 20 Pascal. And what does the vacuum cleaner do? I have a long hose, and this hose picks up the dust over here, dust particles which are smeared all over the floor of this particular carpentry shop. Let us presume that the length of this hose which collects the dust particles and gets into the bag of the vacuum cleaner here is something like, let's say, 4 meters long. Let the diameter of this hose be something like 2 centimeters diameter. Now, I want to find out what is the maximum rate, that means the maximum rate at which the wood dust can be taken through the hose, such that an explosive substance is not formed here, because during the movement of the air and dust I could have sparks in this, and if there is spark, the hose may just explode. I don't want that to happen. Therefore, I want to make sure the mass of the dust particles which are entering the hose, I want to calculate it. What must be the value in kilograms per hour, or let us say so much kilograms per second, such that an explosive concentration is not built with air in the hose. Therefore, to be able to do that, well, I need the data, and the data is minimum explosive concentration of the dust involving wood of size 50 micron size, we say is equal to 0.06 kilogram per meter cube. Therefore, we say, well, it's sucked with a pressure of 20 Pa with respect to the atmosphere, and therefore the velocity of airflow in this particular passage is going to be v squared is equal to twice the delta p divided by the density of air in the medium, that is the velocity. How did we get this? V squared by 2 is equal to delta p by rho, and therefore we say V is equal to under root 2 into delta p by ambient density of air, and I take the value of delta p is given as 20 Pascal, that is 20 newtons per meter square, that is 2 into 20. Well, the density of air is available. The density of air at atmospheric pressure, atmospheric temperature is around 1.2 kilogram per meter cube, and therefore it is into divided by 1.2, and the velocity with which the air is flowing in this duct is 5.77 meters per second. Therefore, but the minimum explosive concentration is given as 0.6 kilogram per meter cube. Therefore, I want to know what is the rate, that is m dot, at which the dust is being supplied in terms of kilograms per second. Therefore, to be able to do that, I want to find out what is the volume flow rate of air, and the volume flow rate of air is equal to Q for air, Q dot for air is equal to pi by 4 into the size of this hole, which is equal to 0.02 square, that is 2 meters square, that 0.02 meter square, into the value of Vt, which is 5.77, so much meter cube per second. And if I assume that the value of m dot dust, which is being sucked over here, is so much kilograms per second, and the volume of airflow is Q dot A, so much meter cube by second, well, I get the value of minimum explosive concentration, and this value is given, we know from data book that it is given as 0.06, and therefore I get the value of m dot at which the maximum value at which the dust can take place, because if it exceeds this value, well, I get an explosive concentration which is greater than minimum. Therefore, m dot dust is equal to, I have 0.06 into pi by 4 into 0.02 square into 5.77, so much kilograms per second, and this comes out to be 0.0109 kilograms per second, or in terms of hour it is equal to 39 kilograms per hour, and this is how we use the data. One last thing, supposing in the same problem, let us presume that the rate at which the wood dust is taken in this hose is, let us say, greater than this amount, let us say it is something like 42 or 43, and supposing by chance an explosive concentration of dust gets built up, and it is given to us that the value of the KST value for the dust is something like, let us say the value of KST for the dust is given as 210 bar meter per second. I want to find out the rate at which the pressure increases, that is the violence, that is dP by dt maximum in the hose, and therefore I say, well, dP by dt maximum into volume to the power 1 by 3 is equal to the value of KST, which is equal to 210. I know that the volume of this hose, essentially it is something like a closed volume, because the opening here is small, opening here is small. Therefore, the volume is equal to pi by 4 into 0.02 square into the length 4 meters to the power 1 by 3 into dP by dt maximum is equal to 210, or rather from this I get dP by dt maximum in the explosion which would occur in case I am drawing more than this is given as 264 bar per second, which is quite a high value. And this is how you estimate the values in the different problems, and therefore to conclude we say, well, dust air mixtures are equally vulnerable to explosions, and we know how to model it, we know how to calculate the concentration when we have feed under gravity. We know when it is being entrained by an airflow how to calculate the concentration, such as done in this particular problem. We also talk in terms of index of the explosibility, we talked in terms of ignition sensitivity, we talk of explosion severity, we talk in terms of minimum ignition energy, and this is all about the dust explosions. In the next class, we will deal with explosions involving flash vaporization. That means physical explosions such as water exploding in the volcano or throwing a bucket of water into a hot furnace. Well then, thank you.